Now we're ready to start Chapter 9. So, in Chapters 1 through 7, we dealt with data collection, descriptive statistics, and probability. In Chapter 8, we formed a bridge between probability and statistical inference by giving us models that we could use to make probability statements about the sample mean and sample proportion. So now we're ready to discuss inferential statistics, right? Making inferences or generalizations about the sample. Okay, we're going to study two areas of inferential statistics: estimation and hypothesis testing. So in this chapter, we're going to do estimation of an unknown parameter, and in the next chapter, we'll discuss hypothesis testing. Okay, so a point estimate is the value of a statistic that estimates the value of the parameter. Remember, the point estimate for the population proportion we had from last chapter is called p-hat. And here's the formula for it, where X is the number of individuals in the sample with the specific characteristic, and N is the sample size. Okay, so in July of 2008, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. So obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. Okay, so our point estimate, p-hat, is simply X over N, where X is the number with the specific, so who are in favor. 1,123 were in favor, and N is our sample size. So they asked 1,783 voters, and that's it. I've got my calculator here. 1,123 divided by 1,783. Okay, so we got 0.6298, and let's agree to round proportions to 3 decimal places, right? So really we're going to say if we round this to this decimal place, that's going to go up to a 10 and make this 0.63. If I need that third decimal place, and really we should probably have as approximately. But let's round to 3 decimal places. So we estimate that 63% of voters are in favor of the death penalty. Okay, now based on the point estimate, the question becomes, can we conclude that a majority of the United States voters favors the death penalty? Or is it possible that less than a majority of voters favor it? Okay, after all, statistics such as p-hat, okay, vary from sample to sample, remember? So a different random sample of voters might result in a different point estimate of the population parameter. Okay, if the method used to select the voters was done appropriately, both point estimates would be good guesses of the population proportion, right? But due to the variability in the sample proportion, we need to report a range of values, including a measure of the likelihood that that interval includes the actual unknown population proportion, right? Okay, and that's what we're going to talk about today. We'll need an interval along with a likelihood that that interval contains the parameter we're talking about. So in statistics, we're going to create an interval for a population parameter based on a guess, right, along with a level of confidence. Now, the guess is the point estimate, so when I say a guess, I don't just mean a random guess, right? The point estimate of the population parameter. And the level of confidence is going to play a role in the width of that interval. Okay, so a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. Okay, the level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted in this format, right? That's kind of the formula for it. It's going to be denoted like 95%, 90%, 99%. For example, a 95% level of confidence means alpha is 0.05. So you'd have 1 minus 0.05, so you'd have 0.95 times 100%, which gives us 95%. Okay, so a 95% level of confidence implies that if 100 different confidence intervals are constructed, each based on a different sample from the same population, we will expect 95 of the intervals to contain the parameter and 5 not to include the parameter. Okay, so in other words, a confidence interval is a range of numbers, like for example 20 to 30. Okay, and the level of confidence is the proportion of intervals that will contain the unknown actual parameter, okay, if repeated samples are obtained. Okay, confidence interval estimates for the population proportion are of this form. It's the point estimate plus or minus the margin of error. Now, the margin of error of a confidence interval estimate of a parameter is a measure of how accurate the point estimate is. So let's say if your p hat, right, your point estimate is 0.5, and your let me get a pen, and your margin of error is 0.03, and your confidence interval is 95%, then that means, so if p hat we were saying is 0.5 and our margin of error, okay, which they're going to call just a capital E here in a minute, is 0.03, then we would have 0.5 plus 0.03 and 0.5 minus 0.03. That's where our interval is going to come from, 0.53 and 0.47. Okay, and if we wanted a 95% level of confidence, we would say that we're 95% certain that the values are between 0.47 and 0.53. Okay, the margin of error depends on 3 factors. The level of confidence. As the level of confidence increases, the margin of error also increases, right? If you're 95% sure of something, you might say, you know, with an error of 0.5. But if you want to say, hey, I'm 99%, your margin of error is going to increase. As the size of the random sample increases, the margin of error decreases, right? Related to our law of large numbers again. The more spread there is in the population, the wider our interval will be for a given level of confidence. Okay, so once again, okay, a 95% confidence interval does not mean that there's a 95% probability that the interval contains the parameter. Okay, remember, probability describes the likelihood of undetermined events. Therefore, it doesn't make sense to talk about the probability that the interval contains the parameter, since the parameter is a fixed value. We already know the parameter. So think of it this way. I flip a coin and obtain a head. If I ask you to determine the probability that the flip resulted in a head, it would not be a half, right? Because I've already flipped the coin. I already know the outcome. The probability is either 0 or 1 after you've flipped it. Before you flipped it, what's the probability it's going to be a head is a half. After you flip it, you know the probability is either 0 if it's a tail or 1 if it was a head. So confidence intervals work the same way. Okay, because your parameter is already determined, we do not say that there's a 95% probability that the interval contains the parameter. A 95% level of confidence means that 95% of all the possible samples include the parameter, and 5% of all possible samples do not include the parameter. Okay, does that make sense? Kind of the distinction, the difference there. We're not saying it's a 95% probability. We're saying we're 95% confident that that parameter is in there. 5% of the time, that parameter is not in there. Okay, so here's their interpretation. A confidence interval indicates that that percentage of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. So a 90%, I can't stress this enough. Okay, maybe you're thinking I'm stressing it too much, but I'm going to stress it one more time for us. A 90% confidence interval for a parameter suggests that 90% of all possible samples will result in an interval that includes the unknown parameter, and 10% of the samples will result in an interval that does not include the parameter. A 90% level of confidence does not tell us there is a 90% probability the parameter lies between the lower and upper bound. The level of confidence is referring to confidence in the method, not in the specific interval, right? An abbreviated way of saying this is that the method is correct certain percent of time, right? The method is correct. Okay, so now we're prepared to present a method for constructing a confidence interval about the population parameter. So, suppose that a simple random sample of size n is taken from a population. Okay, a confidence interval for P is given by the following formula. Okay, note, it must be the case that it's normal, right? Here's our requirements to fit that. It's from the last chapter. We have this formula to make sure it's greater than or equal to 10, and the sample has to be less than 5% of the population to construct this interval. Okay, also in the formula, this z sub alpha over 2, those are called our critical values, right? And the critical value represents the number of standard deviations the sample statistic can be from the parameter and still result in an interval that includes that parameter. Okay, now notice that we used p hat, right, in place of p in the standard deviation, because p is unknown and p hat is the best point of estimate. We also have a formula for the margin of error, and here that's going to be a capital E. So in a certain percentage confidence interval for a population proportion is given by this formula. All right, so we've got our formula. Let's do an example. Let me get my pen. In July of 2008, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1123 were in favor. Now this says obtain a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So step one, we need to compute the value of p hat. So you might want to write these steps down. Okay, so remember what p hat is. Okay, x over n. So x is 1123 and n is 1783. I think we just did this. Yeah, 0.629a. So rounding to 3 decimal places, 0.630. Okay, step 2. Yeah. Okay, verify that our formula, right, to determine, to make sure that it's normal, is greater than or equal to 10. So we have 1783 times, oh, here we are, 0.63. I was looking for it up in the problem, but we calculated it. 0.63. 1 minus p hat would be what? 0.37. Okay, and let's see what that equals. Okay, 415.6. Well above 10. And our sample is 1783 of all registered voters. Again, we don't know the specific number of registered voters, but this is way less than 5% of the registered voters in the nation, right? Okay. So there's step 1. Here's step 2. Now step 3, let's determine our critical value. So let's think about what that means, what we're looking for. All right, remember, because it's normally distributed, then I know this shape applies. Okay, and what we're asking for is a 90% confidence interval. So what that means is this is 90%, and here we want to find the two values where this is 90%. Okay, so if what's in between those values is 90%, then the rest of the graph should be 10%. That would give us 100% of our data, right? But it's split in 2 halves. So this is 5% over here, and this is 5% over here. That's where the alpha over 2 comes from. Okay, that's where the alpha over 2 comes from. So I can always figure out what my alpha over 2 is. All right, so if I want a 90% confidence interval, I've got to find z sub 0.05. That's alpha over 2. Alpha is 10 because 90 and 10 make 100. All right, so now I'm going to look on my chart to see where in the middle of the chart, looking for 0.05. 0.0. Here we go. Okay, sorry guys, but I'm searching my chart and I see, okay, so I'm going to write it up here. I see that when P is negative 1.64, okay, that's at 0.0505, and when P is negative 1.65, it's 0.40495. Okay, I wrote both of these up here because it's halfway. If I just had one that was closer, I would just use that value. But if it's exactly halfway from what I need, right? So 0.0505 is 0.05 away, and 0.0495 is 0.05. If I can't tell, subtract them. This minus this will get 0.05. Okay, and then this minus this, you'll get 0.05. So I need to go exactly halfway in between. So 1.645. And if I don't know what halfway in between is, add these up and divide by 2, right? Take that mean. Okay, and because of symmetry, and because my formula uses plus or minus, right, I can use either one of these. So, but that's my Z value. Okay, so my formula that we're using, remember, is P hat plus or minus Z sub, I'm going to go ahead and put the 0.05 instead of alpha over 2, times the square root of P hat times 1 minus P hat, and this is just a formula that they gave us, over N, that I can now plug into. So we have our P hat, so we have 0.63 plus or minus 1.645. Notice here it doesn't matter if I have a negative here or not, because a negative will give me the plus, and the plus a negative, right? Okay, times the square root of 0.63 times 0.37 all over, what's our N? 1783. And I'm going to put that in a calculator. I'm going to do the minus one first because I want my lower bound first. Okay, so 0.63 minus 1.645 times the square root of 0.63 times 0.37 divided by 1783. Okay, now we can write these bounds. You can either, they might ask you separately what's the lower bound, what's the upper bound. We can write them just kind of in a shorthand notation because we know what we're talking about inside a set of parentheses. Okay, so I got 0.611 on this one, 3 decimal places. And then I can just hit second enter, and all I have to do is go up and change that minus to a plus. And then I got 0.649. Okay. And then finally, let's interpret it. So this means that we are 90% confident that the proportion of voters in favor of the death penalty is between 61 and 65%. Okay, it's important to remember the correct interpretation of a confidence interval. The statement 90% confident means that if, let's say, 1,000 samples of size 1783 are taken, okay, take 90% of 1783, you get 1605. So we would expect 1605 intervals to contain the parameter, while 5% of the 1783 would not. Okay, unfortunately, we cannot know whether the interval we constructed is one of the intervals that contains P or one of the intervals that does not contain P. Okay? Does that make sense? Let me know if you have questions. We'll do another example here in a minute. Okay, think about this. We know that the larger sample sizes produce more precise estimates from our law of large numbers, right? So, suppose you want to estimate a proportion with a 3% margin of error and a 95% confidence level. How many individuals should be in your sample? We got two solutions to that question. Okay, one of them, use an estimate of our parameter based on some earlier study, or just let your parameter be 1/2, since that's the largest possible value, right? Because all of them will be between 0 and 1. The largest possible is 1/2, right? And then you start getting, oh, this likelihood and this likelihood pair up, but the largest is 0.5 that it is in there and 0.5 that it is not in there. Okay, the disadvantage of this one, even though it seems, well, that's easier, but the disadvantage is it might lead to larger sample sizes than we actually need. And because of the time and expense of sampling, it's desirable to avoid too large a sample. So, here's the sample size needed for estimating the population proportion P. Okay, and we got a formula for it. Now notice it says rounded up to the next integer. And of course, P hat is a prior estimate of P. Rounding up is different from rounding off. If we round 12.3 up, we'd make it 13. If we rounded 12.3 period, just rounded it or rounded it off, it'd round to 12. So always round up. Okay? Now, if the prior estimate of P is unavailable, then we're going to use, let me show you why that's 0.25, because this is what I'm going to do. I'm still going to follow this formula. I don't want to memorize another one, but I just need to know that, oh, if that's P. So notice if P hat was 0.5, we said that's one thing we could use because that's the largest possible value. Then 1 minus P hat is 0.5. So they've just simplified that and said 0.25, but it's because P hat and 1 minus P hat are both 0.5. Okay, margin of error, of course, should always be expressed as a decimal. Okay, a sociologist wants to determine the percentage of residents of America that only speak English at home. What samples should be obtained if she wishes her estimate to be within 3 percentage points with 90% confidence, assuming she uses an estimate that was obtained from the Census 2000 supplementary survey of 82.4%. So this means she has a P hat that she's going to use. So that means we would use that first formula. Okay, the formulas are the same. The only difference is what I plug in here. If I don't have a prior estimate, I put a 0.5 in here. If I have a prior estimate, I put that. Okay, so here's the formula from the other page. Okay, so N is, now P hat we know, so 0.824. And then 1 minus 0.824 is 0.176. Okay, now we've got to find Z sub alpha over 2. All right, so again, we might want to think about what that means. Anytime we're talking about Z scores, we're talking about 90%. So we want the middle 90%. Oh, that means this is 5% and this is 5%. So really I'm looking for z sub 0.05, and if I look on my chart, that's the one we just found, 0.05, and we just found it, so why am I, there it is, okay, 1 point, it's negative, but 1.645. Okay, so 1.645 over, now she wants her estimate to be within 3 percentage points. That's her margin of error. 3%, that's 0.03, right? Squared. And then just put that in your calculator. 0.824 times 0.176 times 1.645 divided by 0.03 squared, and I got 436.04. And because we always round up, she needs her sample size to be 437 individuals. Okay, a random sample of 1,003 adult Americans was asked, do you pretty much think televisions are a necessity or a luxury you could do without? Of the 1,003 adults surveyed, 521 indicated that televisions are a luxury they could do without. Okay, so A, obtain a point estimate for the population proportion of adult Americans who believe that televisions are a luxury. So our point estimate, P hat, remember, is just X over N. So that is just, okay, that believe they're a luxury. 521 said they're a luxury out of 1,003. So 521 divided by 1,003 is 0.5194, but rounding to 3 decimal places, 0.519. Okay, verify that the requirements for constructing a confidence interval about P are satisfied. So what they're doing in this example, they're listing you the steps, asking you one step at a time, instead of just like earlier we had that question and just flat out asked the question and I had to realize here's the process of steps I had to go through. Now they've broken it down and asking you each step to consider. Okay, so is 1,003 adult Americans less than 5% of the entire population by far? So then my next question is N times P hat times 1 minus P hat, is that less than or equal to 10? Well, let's see. 1,003 times, now our P hat we found to be 0.519, and 1 minus 0.519 is 0.481. And if we do that, I get 285.481. I put 0.591. Let me go back and change that. Okay, 1,003 times 0.519 times 0.481. This is why it's really handy to have a calculator that shows your entries, because I always look at my entry and double check. For example, that time I had entered 0.591. Okay, and with a quick glance, I was like, oh, don't enter that answer. So I got 250.4. Yes, well above. Okay, well above, or 10. Okay, I'm going to leave these values on here for till we slide to the next slide. See why I always erase them? Just so that we can carry that P hat with us in case we, or should I say when we need it. Okay. All right, now, construct and interpret a 95% confidence interval for the population proportion of adult Americans who believe that televisions are a luxury. All right, so once again, if it's a 95% interval, that means this is 95%. And so what's left over is 5%. And half of 5 means I've got 2.5 and 2.5%. So the z that I'm looking for is z sub 0.025. Z sub 0.025. So I'm looking in my chart to try to find 0.025, 0.022. Okay, I get it exactly. At negative, I'm going to ignore that negative because of symmetry, right? So at 1.96. So now that I know my z value, we've got a formula to construct this interval, right? So it is p hat plus or minus z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. So for our case, this is 0.519 plus or minus the square root, not the square root yet, I forgot to put my z sub alpha over 2 in there. Okay, so 1.96 times the square root of 0.519, and 1 minus 0.519 was 0.481 over, and what was n, 1,003? And then I can just enter that in my calculator. I'm going to do the minus one first again. 0.519 minus 1.96 times the square root of 0.519 times 0.481 divided by 1,003. And I get 0.488. And if I just do a second enter, all I have to do is change that minus to a plus, and I get now I got 0.5499. So if I round that to 3 decimal places, it's going to round to 0.55. 550. I'm not sure how your homework will make you leave that. Okay, I'd take 55. Okay, so is it possible that a supermajority, more than 60% of Americans believe that a television is a luxury? Of course, right? It's possible. Is it likely? Well, we're 95% confident that it's between 49 and 55%. So, okay, it's not likely. Possible, of course. Okay. All right, what about this one? Use the results as C, okay, to construct a 95% confidence interval for the population proportion of adult Americans who believe that televisions are a necessity. So the only thing that's going to change on this is our p hat, right? So in this case, the p hat came from, I do not remember the numbers we use. Let me see if I can, 1,003. Okay, so it's going to be that number, whatever it was, not over 1,003. Okay. Okay, so that was 521 that was, so 482 that's not. Okay, it's kind of difficult to do these when they're on two different pages and you forget your information. But okay, it said we did it to start with on 521 out of 1,003 said that they thought it was not a necessity and it was just a luxury. So that meant if I subtract that from 1,003, 482 of them must have said that it is a necessity, which gives us a p hat for 0.481, rounded to 3 places. Okay, so once again, the only thing changing is the p hat. We still have, because we're still doing 95%, so that's where our z comes from. And because it's still 95%, the z value we have found is not going to change. And look at this. We've got p hat times 1 minus p hat. The only difference is these are going to be in different places. But in reality, multiplication is commutative. So again, I can just go back to this formula that I already have in my calculator and just change the 0.519 to 0.481. 0.481. And then the rest of it's the same. I still have the same z. I still have the p hat and 1 minus p hat. And I still have the same n. So this time we get 0.450 and 0.512. Okay, so this is the confidence interval of the adult Americans who believe that televisions are a necessity. Here it is for those that believe televisions are a luxury. Okay. One more. A researcher for the U.S. Department of the Treasury wishes to estimate the percentage of Americans who support abolishing the penny. What size sample should be obtained if he wishes the estimate to be within 2 percentage points with 98% confidence if he uses a 2006 estimate of 15% obtained from a Coinstar national currency poll? Okay, so this time it's just saying what size sample, right? He knows his confidence interval, he knows what he wants his margin of error to be, and he just wants to know, well, then how big should my sample be? And if you have a previous p hat to use, a previous parameter, then here's the formula for that. And we just have to fill everything in. Okay, so p hat is 0.15, which means 1 minus p hat would be 0.85. Okay, now we've got to find the z sub alpha over 2. So what does that mean? That means this time we want this to be 98% in here. So for the entire thing to be 100%, this should be 1%, and this should be 1%. In other words, it's 2 divided by 2. So we're looking for, okay, z sub 0.01. Because this time we're talking about 98%. So I'm going back to my chart and I'm looking in the body of the chart for 0.01. Let's see where we are. Way up here. Okay. I've got I'll write it up here for us. I've got that negative 2.32 z value is 0.0102. And negative 2.33 is 0.0099. Now, this isn't exactly in the half here. 0.01 isn't exactly in the half here. Here it's off by 2 10,000ths. Here it's only off by 1 10,000. So if it's not exactly half, choose the one it's closer to. So we're going to use 2.33. Once again, I'm squaring it, so it doesn't matter about that negative, right? Okay, so times 2.33, and we want our margin of error to be within 2 percentage points squared. And let's just plug that in. And I get 1730.46. You always round up. So he needs a sample of 1,731 individuals. What if he does not use any prior estimate? Well, the only thing that's going to change if you don't use a prior estimate is you're going to let p-hat be 0.5, right? If you don't have a p-hat, let it be 0.5. So I can go back into my formula, and the only thing I'm just going to do second enter again, and I'm just going to change that first part to 0.5 times 0.5. Okay. And I get 3,393.06. So always rounding up, he would need 3,094 individuals if he doesn't have a prior estimate. Okay? All right. Let me know if you have any questions or need anything at all.